rotational spectroscopy active, or we can say microwave active, when there is a dipole moment, permanent dipole moment. Has dipole moment should be there. Okay. But in the case of the vibrational spectroscopy, vibrational spectroscopy, we need a change in dipole moment. Change in dipole moment. Okay. So the molecule should possess these properties, then only they will be the microwave active or infrared radiation active or infrared active. So then only we can use such molecules in order to study the different vibrational or rotational spectra and corresponding frequency of the bands of the spectra can be studied. So the molecule initially has to be active with this spectroscopy. This means that the molecule should possess dipole moment. So molecule should have some change in dipole moment for this rotational and vibrational spectroscopies. In this case of Raman spectroscopy, so what will happen? This is similar to this vibrational or spectroscopy. We have a change in polarization. So this depends on polarization. Here this too depends on dipole moment, and one should have the permanent dipole moment and have a change in dipole moment. And we have discussed that some of them will be active in some cases, and some of them will not be active. For example, in the case of stretching mode, these two, for example, in the case of carbon dioxide, either rotation as well as in the case of vibration. Microwave, it will be microwave inactive and infrared active, because in the case of infrared, we have different vibrations for carbon dioxide. So those carbon dioxide will be having this stretching vibration like this. So in this case, it is higher inactive, because the change in dipole moment cancels from the side. For example, if it is having a dipole moment, so the dipole moment cancels each other in this vibration spectrum. Okay, so this molecule basically there is no net dipole moment associated with carbon dioxide. When you consider the rotational spectra, because the dipole moment will be cancelling from of the sides from both between this O and C, the dipole moment will be opposite in direction and same in magnitude. But when you consider the other modes, so it will be inactive in that case. When you consider that, but when you consider this case that the vibration, we have this mode is inactive. Okay, this mode is inactive in vibration also. But in the other case, we have asymmetric stretching, for example. So in that case, one will be coming close to this carbon atom. In such kind of case, which means that the bond length between the one arm of the carbon dioxide molecule is stretching and the other one is compressing, like that. So we have a different kind of scenario, and we call this kind of expression as asymmetric stretching or anti-symmetric stretching. So in the case of antisymmetric stretching, we have a change in dipole moment, because in this side we have some dipole moment with this much of magnitude. In that side we have smaller. So there will be some change in dipole moment because of this uh, particular antisymmetric vibration. So antisymmetric vibrations are Raman active. So these things we discussed when we discussed this yes. So this will be inactive, this will be active, and one more vibration mode is there. Two other modes are there. One is and then down to the screen. All those things that we have already. So there are four fundamental vibrations. One of it is inactive, and others are for the case of carbon dioxide. So that we already discussed. So we need some dipole moment and so some change in dipole moment for this rotational angle. Okay, similarly for Raman spectroscopy, we need change in the case of polarization. Okay. So if you consider this kind of scenario, we will first look into the classical and quantum pictures of this Raman spectroscopy. Okay. So because in Raman spectroscopy, what you will observe is that when you are sending a particular radiation to a sample, for example, a crystalline or liquid or gas in gas state, if you send some radiation to this sample, so let's say this is having some frequency mu, radiation is having some frequency, and the radiation which will be coming out from this sample will be the same radiation which will come out with frequency mu. Along with this radiation, we will be having some additional radiation. So some other radiation also will come, and this is, let's say this is mu one. So we will be having some mu two also. We will be having some. So this one is mu two. So when you are sending one particular radiation to the sample, some scattering happens here. This is because of some scattering. So because of that scattering, we call this scattering as Raman scattering. The Raman scattering will happen inside this molecule, and because of that, the in the output we'll get additional frequencies. So this is the basic uh, operation or the basics of the Raman spectrum. So Raman scattering. Okay, this is the basic of the Raman scattering, and we'll consider this in case of spectrum bands. We'll be having one particular band here, much intensity. Okay. So that is mu, and then we can also represent this in terms of wave number. Because, normally consider that in terms of in the limiter inverse. So if you are considering in that form also, so in the case of output spectra, what will happen? We will be having this central frequency, that is nothing but mu. Then in addition to that, we will be having uh, much higher frequency as well as much lower frequency. So we will be having some frequency u2 here, because that will be weak, and we'll also will be having frequency range, but it will be somewhat dense. Okay, what in this figure what means density is the thickness of that line. Okay? How much thick that line that will be representing in the test. So the central line is more intense than the other two lines, and mu1 is more intense than mu2. Okay? This kind of spectra we can observe in the case of Raman because of the scattering of the radiation. So those radiation which are coming out without scattering, without this change in frequency, without change in frequency, these frequencies are called as Rayleigh line. Call them as Rayleigh line or kind of something like that. So this is because of Rayleigh scattering. All other frequencies, one is one, two. These are Raman frequencies. Okay. Because it is arising from Raman scattering, only because of that Rayleigh scattering. So the central one will be having a frequency of mu, and the other two lines are mu plus delta nu or mu plus delta. Okay, so this one is nothing but so this one is nothing but mu plus delta nu. This one is minus. So I'm talking in terms of frequency. You can also represent in terms of the number by using u bar. Okay, so this is the basic process which will happen in Raman spectroscopy. And also we have to explain why this one is, because when you consider the Raman spectroscopy in terms of classical picture if you are considering, it is dealing with the polarizability and polarizability of the molecule. So we cannot completely ignore the classical picture of the Raman effect. But there are some limitations with the classical picture of spectroscopy or Raman effect. So in classical theory, the Raman effect, while not wholly adequate, we cannot take all of those explanations. But in some part of this classical picture, we have to consider, especially the polarizability of the molecule. It's a classical representation. So that part we have to take, but we do not have to consider all of the classical explanation of the answer. Okay, so this is the basic process that will happen in Raman scattering. So if a monochromatic radiation of, let's say, mu, which is incident on this sample, which is used to scatter energy, that will consist of almost entirely of rotations of incident frequency. Okay. So the incident frequency that is also coming out from this after that scattering process, that particular process we call it as the Rayleigh scattering. But in addition to that, certain some other certain above and below this frequency mu also will be coming with this radiation. Those are called as Raman bands. So when you are representing that in terms of so this is the Raman scattering. Now, first we look to the quantum mechanical explanation or quantum theory of Raman scattering. Why this is happening? That is through quantum mechanical picture. Okay. That we will discuss first because it will give a much more clear idea of the basic process behind this Raman scattering, apart from the classical picture. So because but in case of polarizability, we will use the classical explanation of polarizability change and all those things, polarization, all those things. So first, we will consider the quantum mechanics or quantum theory of scattering. So remember, this is the scattering process of the radiation when it is passing through the. So let's say the quantum theory. This is not that much. We are not going to that much deep to this. So we will just explain what Raman said. Okay. So the occurrence of this Raman scattering may be mostly uh, we can understood it very easily in terms of quantum theory of radiation as compared to the classical picture of the same. So this treats radiation of frequency mu, which as consisting of number of photons uh, they are having energy h nu. Okay, so if we are having that radiation, instant radiation, which is coming and hitting on this molecule with the frequency of mu, then the corresponding energy will be h. You know that. So those radiations which will be, or those photons which will be uh, interacting with the molecule, and this radiation will be having this mu, is having a frequency of mu. Okay, and these photons can be that can be imagined going collision with the molecules when uh, they pass through the molecule. Okay? And if the collision is perfectly elastic, means that all energy will be the transferring of energy should be elastic. So when it is perfectly elastic, there will be deflected unchanged. A detector placed to collect the energy at right angles to the instant will thus receive photons of energy. So, which means that the same radiation frequency that we can observe if the scattering is elastic. Okay. However, if it is inelastic, which means that it may happen that the energy is exchanged between photons and molecules during the collision. Okay. In that case, the collision will become inelastic because energy transfer occurs. When that happens, in such case, such collisions are termed as inelastic, and the molecule can gain or lose energy. Some energy will be transferred to the molecule, or uh, molecule, some energy of the molecule can be taken by the photon and coming out. So both of these can be possible. And according to this quantum theory, this will not happen in continuous fashion. Instead of that, this absorption of energy or by the photon, or we can say by the molecule, either way. So the absorption of energy by the photon from the molecule. Similarly, the energy absorption of the molecule from the photon. In both cases, the energy will be transferred in contrast, okay, which means that all the energies, or all forms of energy, the energy cannot be a continuously distributed function, which means that, for example, if you are having this photon which is incident, which is going to pass through this particular sample, this sample can take energy from this photon, or the sample can give energy to the photon. Both are possible. And this energy exchange will not happen in a continuous fashion, which means that the energy exchange will be happening in terms of quantas, which means that some particular energy will be giving by the photon to the molecule, and next time it will be having some, it has to be some energy, it has to reach to some energy, then only it can show that energy again. So it will be in some kind of quantized states or quantization of energy that will be transferred into the molecule. Similarly, the molecule will be transferring energy into the radiation quantas. So which means that we will not be having a continuous distribution of that spectral line. Instead of that, we will be having some spikes. That's why we are getting some mu and mu1, mu2 like that with some specific frequencies, because the energy transfer is happening in terms of quantas. So there is no continuous distribution of energy, like we can see in classical picture. We have a continuous transfer of energy. If it is, for example, 1 joule, this is just an example, so, or we can take any other. So if you are considering 1 joule of energy, then in the quantum in the quantum theory, we do not have 1.2, 1.3 like that, but we have from 1, then it will go to 2, then it will go to 3, then 4 like that. In between, there is no energy transfer of those. But in the case of classical picture, if you can take any value of the energy, you can take 1, 1.1, all those. But this kind of energy transfer is not possible in case of quantum theory. So because in quantum theory, we have concept of the condensation of energy, and all the photons will be having the photon energy, which is packets of energy. Right? So the radiation transfer also will be in quantas. So the transfer will be occurring a particular energy when the radiation is having. And we can also associate this kind of energy levels associated with the transfer. Uh, Actually, in reality, there is no such energy level, but for representation, we will use energy. So if the molecule is at this position, for example, E1, then it has another energy level, which is E2. In between those E1 and E2, there is no energy level. So the molecule will go to this E2 energy level only if it uh, receives the radiation of this energy gap E1 minus E2. So this incoming radiation, which is when it is equal to that of the radiation, the energy levels, then only it will absorb that energy. Okay, so that is the condensation of energy absorption by the molecule. So the molecule will be absorbing like that. Similarly, the molecule will be emitting the radiation by coming back to the, and it will be giving radiation to the photon. So both of this can be possible, or both these are possible. So we will be having this. So by means of this, we can say two possibilities in terms of frequency of the photon. The photon can absorb energy from the molecule. So photon plus energy will come. Okay, this energy has been received from the molecule. So this will give you h nu plus some other h nu. Let's say some 1. And in other case, the photon can reduce some energy, which means that the photon gives some energy molecule. In that case, this will become H nu minus. I'm just representing. So this was when I'm using the last figure. Anyone? I don't have any picture of that. So, okay, let's say this is the stock line. Okay, in this case, if you are considering this, this will become the stock frequency. There will be addition of energy, as well as we have there is a decrease in reduction in frequency. Both are possible. It can the photon can give energy to the molecule. The photon can also absorb energy from the molecule through this scattering process. So by means of quantum theory of radiation, we have this kind of explanation. So when it is absorbing, we have a total of h into nu plus nu 1 will come. And then when it is reducing its energy, then it is h nu minus h nu 2. And this one is called as Stokes line, or we will discuss that in that figure. Anyway, so this is h nu 1 and the other one is h nu 2. Okay? And let's put it in that frequency band again. So we have that central frequency is much more intense, and we have a very weak dense line at this point. So this is your mu2, and this is, or if you are taking the frequency this direction, then okay, the energy should be reduced. So this one will be mu1, because that is high energy. So it depends. So mu1 and mu2. So which means that when the molecule give energy to the it can give energy to the radiation. Also, it can take energy from the radiation. In both cases, the energy can be reduced. The energy can be increased. Both are possible. So that will happen in this case, and the correspondingly. So okay, right. Okay, in this fashion. So some of the energy I should write this as some, write it as some delta E. So this will get some energy delta E. This will be having some less energy from the nu, because it will give some energy to the. So the frequency has to change. That's why I have replaced this expression, because from this we will get to that h nu1, and so that's why I'm replacing this. It's not h plus h nu1. Of course, that will be some energy which has to be added up with it, and some energy has to be subtracted from h nu, and we'll get to some different energy for the photons h nu1 and h nu. So basically, the energy of the photon means that the frequency of photon will be getting changed because of this inelastic pollution. So that is the process. So we'll be having h nu1 and h nu2, and also we will be having that h nu which is coming without having any interaction, which is nothing but the elastic collision of the photon with the molecule, there is no energy transfer. But when inelastic scattering occurs, which means that there will be energy transfer between molecule and the photon, in that case, we'll be having some change in the incident frequency, change in and those photons which are having much higher energy, uh, then they will be having higher frequencies. Okay? And those lines or the frequencies which are higher than those of nu, which are called as anti-stop lines. In this case, we can term this line as and this is called as stop. And anti-stop lines are much less intense as compared to the stop lines. We will discuss why it is less intense as compared to the preceding section. So the anti-stop lines are less intense as compared to the stop lines, and the central frequency will be much higher. So this is the quantum mechanical or quantum theory of Raman scattering. Okay. So the radiation scattered with a frequency lower than that of the incident beam, which is called as Stokes radiation or Stokes line. When you're representing that in spectra, it is Stokes line. When it is talked about in terms of frequency, it is the Stokes radiation. And while that of that at the higher frequency, which are called as anti-Stokes line, because the molecular energy is also related to molecular, because when we have this interaction molecule in terms of molecule, it will have a reduction in energy as well as it will be having in terms of molecule also it can be defined. So anyway, so we will define in terms of the radiation, and the Stokes radiation in general more intense than the anti-Stokes lines. Also because we'll also explain that why these Stokes lines are more intense than the anti-Stokes lines. Okay, now that is the quantum mechanical picture of the quantum theory of Raman scattering. Now we'll look into some important section by classical theory of the Raman scattering, because I don't think you have to study the classical theory of Raman scattering completely, because some of the explanation is that much satisfactory in terms of as compared to this quantum theory, which is a little bit more easy to look at. Otherwise, you had to look into the classical picture. It is going to explain the classical picture of the radiation from the basic equation of the incoming radiation and all those mathematics. That also the in classical explanation of the but we are not going to look into that explanation because it is much more complicated and it is not that much important for you. So we will be considering quantum theory of the it is also now, but we are not completely we cannot eliminate this classical picture because classical theory has one important thing, that is the molecular relation between the molecular polarizability or molecular polarization with the Raman scattering. So that we have to consider. So we will explain the classical theory of Raman effect. Okay. Classical theory of Raman effect. And in this theory, we will not consider all those derivations associated with how this slope line and this slope line are coming. That we are not going to discuss completely. Okay, but some point we will do that. But in this case, classical theory of Raman scattering, we are more focused on those molecular polarizability. Molecular polarizability. Okay. So in case of as I discussed earlier, in case of a classical theory of Raman scattering or Raman effect, uh, that is worth consideration since it leads to an understanding of basic concept to this Raman spectroscopy, how it is happening, what is the basic uh, changes, what is the basic physical change or physical quantity that is changing inside the molecule that is resulting in this Raman spectrum. So in terms of in case of microwave spectroscopy and IR spectroscopy, we have the physical quantity, which is the dipole moment, which is the reason or the core of those spectroscopies. And similarly, what is the core physical change that is happening in Raman scattering or in Raman spectroscopy that is leading to this Raman spectra that we have to consider. And that is well explained uh, in terms of this polarization or polarizability of the molecule in the classical picture of Raman scattering. So because of that, we will be discussing uh, some of the that important facts which is explained in the Raman scattering, uh, sorry, in the classical picture of Raman. So when, for example, a molecule put into when a molecule put into this electric field, that is the basic idea behind the polarization that is discussed. So when you put any molecule, sometimes you will be having negative and positive charge in the then when a molecule is put into the electric field, and then because of this electric field, it will be having some disturbance. This molecule will be having some disturbance, and the positively charged nuclei, okay, being attracted towards the negative pole of the field, and similarly those the electrons, electron cloud, that will be attracted towards the positive pole, and the separation uh, of these charge centers because of the induced because of that electric field, that will induce an electric dipole moment to be set up in the molecule is said to be polarized. Okay, so the size of the induced dipole moment depends upon the magnitude of that incident electric field, and on the case of it, can represent that as mu equal to alpha into E, and this alpha is the polarizability of polarizability, which is nothing but the ability of the electric field to polarize that particular moment. Okay? I hope you know these things because these are the basic ideas. Okay, I will just represent that story. if you are having any molecule in your sample, and if you are sending some electric field through this sample, what will happen to this molecule, or if you can simply consider an atom in case of atomic, if you are considering that in terms of atoms. So when a molecule is put in this electric field, okay, it suffers some kind of a disturbance, and the positively charged nucleus, cannot say, because it will be having number of atoms, so we write nuclei. So the positively charged nuclei are attracted to the negative pole of the field, and the electron to the positive pole of the field. So the separation of these charge centers will happen inside this molecule, and that will create inside the molecule, that will create some kind of induced dipole. So that will create some induced dipole moment. Why induced? Because we are applying this electric field and creating that dipole moment. That's why it is called as induced dipole moment. And also, in some cases, this will be there inside the molecule, or it will be inside that atom naturally. That is also possible. Okay. So and if you consider that induced dipole moment, that we can represent like this mu. This is nothing but that induced dipole moment. Okay, so the induced dipole moment, I would like to dipole moment. So induced dipole moment mu will be equal to alpha e. This alpha is the polarizability. Polarizability. If this writing is not good, so this is polarizability. So polarizability means that how much it is easy to polarize, okay, the molecule. So that quantity is represented by alpha. It's a constant, and it also depends on that electric field, applied electric field. So dipole moment, in this dipole moment will be depending on the strength of electric field applied, as well as the polarizability of the molecule. So for each of these molecules, polarizability will be different, which is nothing but the ability of the electric field to polarize a particular molecule. Okay? So for each molecule, this polarizability will be different. Okay. So for example, if you consider diatomic molecules such as hydrogen, in your case, it is example as given as hydrogen, and the polarizability is anisotropic. That means that electrons forming the bond are more easily displaced by an electric field applied along the bond axis than the across the direction of the bond axis. So it is anisotropic in that case. And in the case of uh, what it means is that if you are considering hydrogen, example, so hydrogen will be bonded like that. And if you are applying electric field in this direction, for this case, and the polarization that will be produced by this in this molecule, which means that induced dipole, making that induced dipole moment inside that molecule by applying the electric field, that will result in polarization. And that polarization, I think, will be given by epsilon 0 chi this expression. So this is the induced dipole moment. If you are considering that per volume, unit volume, that will give you the polarization. So the polarization also directly proportion to the induced dipole moment in that particular molecule. So what we are considering is that in this scenario, what we are considering is that consider that diatomic molecule, let's say hydrogen, and apply electric field along the axial direction of this bond. Okay, so those electrons which are creating or which are bonded in both of these hydrogen, if you are considering that as an atom, like this, these electrons which are bonded together, okay, and these electrons are which can be easily pulled apart, okay, which means that it can be these electrons can be separated, which means that we can have some kind of a displacement of these electrons by applying this electric field. As we discussed earlier, the electrons will be attracted towards that positive side of the electric field. And in that case, it is easy or it is higher when you are applying electric field in the axial direction. Okay? But when suppose your hydrogen's position, let's say the hydrogen is like this, and you are applying the electric field in this direction again, and in this case, the molecular polarization that will be less, because this is the same when you're considering that the dipole moment when you're considering that axial and perpendicular case, equatorial case. When you're in that case also we have studied the same kind of explanation from the +2 classes itself. So the same we can apply here. When you are applying the electric field along the axial direction, we'll be having more polarizability or more polarization as compared to the second case when you are having an electric field which is in the different direction. Okay, and how we will represent this electric field or in the polarization which is there in the molecule, how we can represent easily. So then we have to use a new kind of concept for U, that is the polarizability ellipsoid. So in the case of polarizability ellipsoid, for example, if you consider this hydrogen atom, sorry, hydrogen molecule, so this in this case, for example, in this it is having some direction like this. Okay, and in these two cases, if you are considering, then the polarizability ellipsoid, okay, it is figure is here. So the polarizability ellipsoid will be different. So this is the polarizability ellipsoid of this hydrogen molecule. So if you are applying the electric field in this direction and we have maximum polarization in the axial direction, we discussed it. Okay. So where the polarization is maximum or where the polarizability is maximum, okay, either the radius of the polarizability ellipsoid will be small. So if you are considering this particular direction, the radius is small, this direction. Okay? Because the polarization is or polarizability is larger in this direction of because the axis is that the hydrogen molecule axis. Along the axis, we have to apply the electric field. Then polarization will be very large in that particular direction. But if you are considering this direction perpendicular to this axis, if you are applying this electric field, then the polarization will be minimum, so that in this direction of this ellipsoid, the radius will be large. Okay. Remember that where you are having the polarizability is which is larger, in that direction, the polarizability ellipsoid will be having smaller radius. And vice versa, which means that if you are having smaller polarizability in some particular direction, there you will be having larger radius for your polarizability ellipsoid. Okay, and this is a three-dimensional thing. I don't think that it is a two-dimensional circle like that or ellipse like that. This is a three-dimensional figure, and also it is an ellipsoid. It is not an ellipse; it is an ellipse. So when you consider this in this direction, we have the polarizability which is large or smaller, so that the radiation is higher. Okay? Because when you are applying electric field perpendicular to the axis, then the polarization will be smaller. When you are applying the electric field parallel along the axis of this polarization will be larger, the polarizability is larger. When the polarizability is larger, uh, the distance or the radius will be small. And I think it is having some proportionality. I don't remember this R proportion to 1 by, anyway, it is 1 by root alpha. Okay, so it will be proportion to 1 by of that. So it is inversely proportional to that molecular polarizer. I will confirm this equation, but it is like this R is proportional to 1. Okay. So anyway, that is polarizability is inversely proportional to the radius of this ellipsoid. So where the polarizability is larger, we will be having smaller radius. So if you consider here also, you are applying electric field in the same direction, for example, in this direction. In that case, we will be having some kind of polarization which is possible, because in that case, but it will be less than that of this case, because you are not applying the electric field along the axis of that molecule. So there will be polarization, but it will be smaller, so that your ellipsoid radius will be increased as compared to this case in that direction. Similarly, if you are considering the perpendicular direction, which will be like this, if you are considering electric field in this direction, so in that case, which will be much less polarization as compared to the axial direction. As you can see from here, in this direction, we have very small angle here. Okay, so it is deviated from that axis with a small angle. So there will be some polarization. Of course, it will be less as compared to the first case, but it will be having some kind of polarization. And because of that, the polarizability also will be higher, but that polarizability is smaller than the previous case. If I consider electric field axial polarization is alpha A here, and electric field axial polarization alpha E2. So this is alpha A1, this is alpha A2. So the axial polarization, if you consider from these two, then it will be alpha A1 will be higher than alpha A2. That is right. And since because of this, we are considering in axial case only. Okay? So because of the angle which is making with the electric field, the axis which is making electric field, the polarizability will be less in the case of this second case. This case, talking about this case. Okay, so alpha A1 will be greater than alpha A2 because we are not applying the electric field along the axis in this case. So because of this, as R is inversely proportional to that 1 by root alpha, because of this fraction which is going to vary, or the radius is inversely proportional to this molecular polarizability, and because of that, the radius of the axial case A1 for the first figure, this axial case, so the electric field, this radius is A1, or you can call it as minor axis or and this will be less than that of RA2. So you can see that. So this RA2 will be larger than. And similarly, when you consider the other part, also in the case when you are applying that in the perpendicular direction. So if you are considering that in the perpendicular direction, also we will be having some polarization, but it will be less. Sorry. In this direction, there will be some polarization, and also that we have to consider. But because of the angle, we have to if you want to clearly picturize that, it will be little difficult to picturize because we have to look into in different directions. We will examine this in the case of vibrational, also vibration spectra when it comes. Sorry, I'm talking about Raman spectroscopy. So, like in case of IR spectroscopy and in microwave spectroscopy, we have a condition for Raman spectroscopy also, that the molecule should be having some change in polarizability, change in molecular polarizability. Then only that molecule will be the Raman active. Then only it will be Raman active. So in this case, if you consider, we have different polarization at different positions of these hydrogens. Okay. So when you, for example, when you consider this state, the hydrogen position is here, and you are rotating this molecule about this axis, okay, is passing through this oxygen, like as we discussed earlier, like you are spinning this device, okay, something like this. Similarly, we are rotating this particular water molecule. When you are rotating, this hydrogen is coming out of that plane. This oxygen is going beyond to inside that plane of this green. If you are considering like this hydrogen you will not see because it is inside that plane. This hydrogen is coming out of that plane. So in that case, you have made some rotation, and you have made some rotation with an angle like this, and this hydrogen which is coming out of the plane. So you have made some theta, and the electric field also which is going in direction, for example, axial direction. And in that case, okay, if you consider, I'm not talking about this. This electric field is not in axial direction. This is the axis. I should write along the axis of this bond. Okay, because we have one more axis here, because this is the center of symmetry, axis of symmetry, okay? Symmetric axis, or we can say. So, axial means, I'm talking about axial means that along this axis. When I'm saying electric field along. Okay? So we are talking about this axis. Anyway, so this electric field, for example, which is applied like this, then it is going to make an angle with this hydrogen, so that the polarization will be getting decreased as compared to this case. Because we are applying the electric field, here we will be having angle like this. Okay. So in this case, the angle, we have to consider the angle in a different manner, because that hydrogen is shifted in this direction. So in that case also, we will be having some change in the molecular ellipsoid, polarizability ellipsoid, like that. And also, if you are applying the electric field in this direction, so what basically happens is that with the rotation, we have some change in molecular polarization. Okay. That is the important thing, in which direction it is that. But you are having some change in polarization with the rotation. Similarly, when you consider this vibration of this hydrogen molecule, it means that this hydrogen is going this side, this hydrogen is going to this side, in that plane itself, in the plane of this green. Okay, this is the wagging, right? So this hydrogen is going to this way, this hydrogen is also going to this way, and again it will come back. Okay. So then this hydrogen will be reaching at this position, and this is the bending mode. And this hydrogen, that will come back to its original position and again go to that position. So this is some kind of vibrational motion of the water molecule. And in that case also, when you consider with the initial case, if there is a vibration like wagging, as we discussed here, we have a position of hydrogen which was having initial position. This position is here, and it is going direction and coming back and again going. Okay, so this kind of vibration, bending vibration is there, and because of this bending vibration, we have a change in polarization. Okay, because of that change in polarization, we have this polarization tensor. We have change. So because of rotation also, as well as because of vibration, we will be having a change in polarization. Okay? So along with the polarizability of the molecule, okay, the molecule has to be polarizable. That is the first condition. And then we should have a change in polarizability. Then the molecule will be Raman active. So we will discuss more about the how the rotation is going to affect the spectra, how it is coming, or what is its position, or what is the selection rules, how the transition, all those things that we will discuss in class. So if you are having any doubt, you can ask. I will look into more, or you can look into more into this molecular answer and point. Uh, it's not a big deal, I think, because normally questions coming from our side, but for presentation or sometimes